Recording is rolling. It is Wednesday, October 23rd. Oh, I think it's mole day in chemistry. So you guys picked up your forces quiz from your return folder. So I got this back to you guys. If you want to do corrections, you can do corrections. Same as always. I'm going to create a bonus column in quarter two and just put that bonus column quarter two. All right. So today, let's do a bunch of demos and puzzles related to your last couple of labs. All right. So there's a centripetal force lab. We'll hit a review on that. Before that, you guys do this turntable lab. By the way, that lab page, put those labs on it. I did also grade and get back to your folder, so that should be back here too, right? If you wanted to follow along with there. We're just going to do a bunch of examples. Right, so here, let's start with this guy. So you guys remember this? If there's some mass going around some circle, if you know the radial size of the circle. So if you know this mass, you know this radial size, okay, and you know how fast it's going speed, there has to be some inward acting force, maybe like a tension in the string to hold it there. And I'll call it centripetal force. You guys remember that? So let's do a numerical example. Suppose, right, you guys ready for this? No, numbers? You guys ready for some numbers? Suppose this mass going around is 1 kilogram. You guys got that? 1 kilogram. And it's in a circle with radius size 1 meter. So you hold up the meter stick and it's exactly 1 meter stick, 1 meter. 1 kilogram at 1 meter. Let's say it's going tangential speed at 1 meter per second. So you point a radar gun and read at it, it reads exactly 1 meter per second. Right? And let's simplify this and say this is horizontal. Either the string could be horizontal, or maybe it's not even a string. Maybe it's just a rod, right? Which is still pulling in with some tension force. Okay, you guys got all that? All right. Right, so got a flat circle, 1 kilogram mass, 1 meter radius circle going at 1 meter per second. Question, what is this tension force equal to? 1 Newton. Yep, there you go, 1 Newton. Because all you have to do is follow this formula right here. This is the answer to your lab. Oh, we did, right? So put a 1 kilogram here, 1 meter per second here. Now let's see if you get squared, but 1 squared is still 1. Divide by 1 meter. Yeah, if this is 1, 1, and 1, it's 1 Newton. It takes 1 Newton of inward pulling force. Okay, you guys got that? All right. Oh, how about the cup with the water in it? Yeah, let's do that demo again. So I got a cup, got some water in it. And I did this before this lab, and then after you guys did the lab, I said, hey, we can take this equation, we can solve with the cup with the water in it. I got a string on this cup. I'm going to whirl this around in a vertical circle. All right, now at the top of the circle, the water is upside down, the cup's upside down, right? But the water doesn't fall out. Ooh, because it's going around fast enough. We'll have to go a little slower, a little slower, a little slower. You guys remember doing this the other day? And at some point, there's like a minimum speed to make sure that the water stays in the cup, right? Which actually I got this next poster here and cover up part of this. See if you guys can solve this from scratch. There's my picture. Actually, I really care about that top picture right there. Just showing a ball on a string, could be water in a cup. Same idea, maybe same math. Okay. So I'll throw some numbers at you guys. You guys can put this in your notes. Let's do water in a cup and a vertical circle or a vertical loop. Okay. So here's a cup. It's got some water in it. Draw a little fish right here. So you could think about it from the point of view of the fish if you like. Maybe that could be helpful. Hey, let's put this on a string. Here, this has been working good all day too. Look at that later. Okay, put this on a string. Okay. So that it's following a circular path. So I'll dash off. It looks like a circular path. Like that. Okay. It has to be going some speed. I'll call that V for tangential velocity. It could be a speed. You got that? Right. I need to give you guys some numbers. I'll give you guys Earth gravity is, let's call it 10 meters per second squared. We got that. I'll give you guys the radius of the circle. I'll call this radius equal to, how about 40 centimeters? That's pretty close to actually what I have with this cup and this string is pretty close to that. Okay. I'll give you the mass of the water here. Let's say the mass of the water is, 50 grams. 50 grams of water, right? What is the minimum speed? Can you guys solve for that V? Go ahead. You solve for that V. What's the minimum speed to guarantee that it gets around the loop? All right. Give you guys a little time. All right, so we solved this one the other day. See if you guys can still solve this from scratch. Give me today. You guys solve that. Okay. About a 40 centimeter radius. Earth gravity 10 meters per second squared. Throw in 50 grams of water. What's the minimum speed? Make sure that it gets around. Say, does anybody know? Maybe I'll help you guys out a little bit here. Okay. How about a free body diagram? Could maybe be helpful. Okay. So if I throw a mass dot right there, okay. Do you guys think there's some weight pulling straight down? Mg? Mg. I got some mg, some weight pulling down. Okay. Now, if it goes around with sufficient speed, do you think the bottom of the cup is providing an additional normal force holding the water in? Yeah, that would be true. Keeping it on this curved dash line path. But if we're talking about a minimum speed, it's just barely getting around, then what is that normal force approach? 0, right? Or in my poster version, I have a tension in a string with the ball, right? That would still approach 0, right? So actually, that one force I just drew in pink ink with that mg, that's really the only force at that moment that's keeping this mass of water on that curved path. That's the only force. That's it. Maybe that can help. Maybe you guys remember back to, I said we have to solve your lab before we can answer that question, so it's probably something to do with this formula. Here's the formula for the force keeping something on a curved path. And here's the force that is keeping it on a curved path. Yes, I see. That might be that. Okay, you guys got that written down? Got two perspectives on this force. Okay. Need some force to keep something in a curved path. That's mv squared over r. The only force I see doing that for the cup of water is, well, just its weight at that one moment. All right, did anybody solve it by now? How fast do I have to swing it? Yeah. So I'm going to say that the centripetal force, F sub c centripetal force, is being provided by the gravitational force. Centripetal force, guys, what's an expression for centripetal force? mv squared over r. And then gravitational force, that's weight, that's m times g. Okay, I'm solving for v. Okay, you see that? Let's go ahead and solve this one in terms of variables first, and we'll plug in the numbers after the fact. So if I want to solve for that v, I need a couple of algebra steps. Guess what's the next algebra step? Due to both sides. Yeah, cross multiply the radius. Okay, so now mv squared equals mgr. Okay, what's the next algebra step? Does anything cancel out? The mass. Goodbye. And what's the last algebra step? Square root. Right, I should say minimum speed, so I throw on a subscript minimum. Yeah, it's the square root of everything left over, which is, okay, I got a g and I got an r there. Right? That right there is the general solution that could solve any of these. So I guess you could have any radius circle, and for that matter, you could be on any planet, because gravity field is part of that. Right? Hey! That's the part I was covering up. That's that right there. Look at that. Square root gr. I just went ahead and solved it right here. Right? Same thing. Let's plug in some numbers. So v minimum equals square root. Okay, we got 10 meters per second squared for g. I got a radius of 40 centimeters. You guys see radius of 40 centimeters? Should I go plug into my calculator? Oh, I'm going to plug in 40 for r. Should I do that? Guys, if I plug in 40, what am I saying in my calculator? 40 what? I want centimeters. If I want to plug with the equations, can I do centimeters? after you choose what? Meters. Guys, how many meters is this equal to? 0.4. So 2 decimal places is 0.40, and that's meters. Okay. Now I can do a calculation to get how many meters per second for the speed. Okay. So square root 10 times 0.4. V minimum equals, the answer is 2. Wait, or is it? It's 2 what? Can I just say 2 and walk away? 2 meters per second. That's what I'm looking for. Units. Meters per second. Okay. Guys, don't forget your units. It's a physics class. All these numerical values have units attached to them, so they mean something. Okay. 2 what? 2 kilograms? 2 miles per hour? No, 2 meters per second. That's what we're looking for. All right, you guys got 2 meters per second? All right, get ready for the next question. Next question. We're just going to do a bunch of these questions all day today. That's a good way to do this today. It's time to go on a roller coaster. Guess where you go on a roller coaster? Right, roller coaster. Okay. So say there's a big old hill on this roller coaster, and it's going to plummet down and then go into a circular looking track. And then on it goes. I'll come back and talk about the circular track later, but let's just do the math first on this one. So got this roller coaster at the top of the hill, plummets down, whoosh. And at some point where it's most vulnerable to fall off the track, that's when it's right about here. Right about here. Right. Oh. And, ooh, guys, could this roller coaster be stationary at this point? Or does it have to be in motion to make it around? It better be in motion. Right? I'm going to ask you the same question as I asked before. What is the minimum speed? I'll label that V for tangential velocity. Right? So you guys saw for the speed, right? How fast, right? I'll give you guys Earth gravity again is 10 meters per second squared. Let's say I tell you, here, I'll do a little tricky here. Let's say the height of this roller coaster loop, the height of the loop is, I'll call it lowercase h. Let's call it 50 meters. So this whole thing is 50 meters tall. 50 meters tall. Okay. How fast do you have to go to make it through that loop? Oh, wait, did somebody say it? At least got it. 15.8 meters per second. Okay. How'd you know that? How'd you solve that? Yeah, it's the same question as the water in the cup. It's the same thing, right? Except instead of there being, say, a normal force from the bottom of the cup or a tension in the string, now it's possibly a normal force from the track, right? So if I do a free body diagram on this roller coaster, it's definitely got a weight that's trying to make it fall off the track. I'll label that mg, right? Now, if it's around with sufficient speed, do you think there's also a normal force from the track that's also pushing down, right? That would be true, right? But if you go a little slower until it just barely gets around, that normal force goes to 0. So I'm just going to leave that right there, right? And then, yeah, it's just the exact same math as all this, which we just did. So I can just cut straight to the solution, cut, skipping a bunch of steps. The minimum speed is always just square root GR. That's it, right? So let's get some numbers. So square root, you can do 10 meters per second squared for Earth gravity. And for R, hey, what's the radius of the circle? 25 meters. 25 meters. I've seen this quite a few times. Physics textbooks like to do that. Say, well, here's the height of the loop, and then have you guys figure out that, the radius would be half of that. Right? Height's the diameter, radius is half of that. You guys see where I'm getting 25 meters? Right? So the square root of 250, what's the square root of 250? That's V minimum equals 15.8. It's 15.8 what? Meters per second. There you go. So you have your units. Right. That's how fast I have to go. How about, I got some follow-up questions on this one. What if this was an empty roller coaster. So we're going to test run it in the morning. Let's say we've been test running these roller coasters and they haven't been going fast enough and they keep falling off the track. Right? But that's okay. They're empty. Nobody's getting hurt. Right? And then finally, we get one going. We get just fast enough, just barely gets there. And at the top, it's going 15.8 meters per second, and it makes it around. It just barely makes it around. Like, oh, shoot, finally, we got this to work. Right? Maybe it's not the best, but it just worked barely. Right? And then, it's time for the park to open. The park doors open. Everybody lines up. I want to go on that roller coaster there. And they all line up and they all line up there. Right? And then we're setting this thing, ready to go. And then let's say the president of the amusement park comes over, says, hey, that does work, right? Oh, yeah, we got it working this morning. It's going 15.8 meters per second. Oh, wait, but it's full of passengers. So now it's twice as massive as before. Oh, no. Guys, now what's going to happen? Is it going to still make it around now that it's full of passengers and it's twice as massive? Show of hands. Who says, yes, it's still going to make it? Still going to make it. Yeah, you guys got it. How'd you know it was still going to make it? The mass canceled out. Mass is not part of this equation. The mass, it canceled out here, right? Actually, I should have said that with the water in the cup too. Let me go back a few minutes ago. You guys remember I gave you guys 50 grams of water in the cup? Do we ever even use that? No. What if I went back and put more water in the cup? Would that change it? No. As long as the radius doesn't change, but probably not so much. Okay. Yeah. So I think the answer would still be the same. That'd be the same. That'd be the same. Yeah. So we're good. We're good. Okay. How about this? You guys see the height of this hill right here? Suppose I call that capital H. I call this capital H, that drop height. It's that drop height, capital H. Okay. What if you're increasing that drop height? So I have a short hill, a medium hill, and a tall hill. I'm making this taller, taller, taller. Do you guys think the taller I make this hill, the faster this roller coaster is whiz around that loop? Do you guys think? Yeah? Does that make sense? Right? Right. And if you have to target a specific minimum speed, suppose this speed, and let's say you have negligible friction loss, do you think you could calculate the minimum height of the hill to make sure that it matches this minimum speed? Do you think you could do that? Right? Right. So hold on to the idea. We're not going to solve that today, but I want to plant that idea now. When we get to conservation of energy a few weeks from now, we're going to answer that question. Okay? So hang tight on that. I got another follow-up question. Actually, let me find my notes from earlier today. I'm going to show you guys these notes here. You guys see how I made this like a circular track, right? If you go on modern day roller coasters, they aren't actually shaped like that. They were shaped more like this bottom picture, right? Now, go back 100 years ago to the 1920s, they started off making them pretty close to circles, like get straight out of the physics textbook. But modern day roller coasters, they actually build them these teardrop shapes, right? And this is a better design. Now, here's a good application question, or well, see if you guys can figure this out. Critical thinking question. This is a good critical thinking question. Why do they build these roller coasters with a teardrop shape? Why not the actual circle? Kind of a tough question, but some students have got this today. All right. All right. Yeah, Isabel got it right away. Yeah, it's yeah, let's here, guys, it's like this. I'm gonna walk you through this. Suppose you did have a circular track, right? You come down this hill, right? Now you're on a flat track for a little bit. Okay, flat track. Hey, is that like being in this room or being on the interstate? Yeah, just go on flat. You feel 1G. And then you hit this circle. And when you hit that circle, boom, this just pops up out of nowhere. And it's really jarring. It's like just going on, da, 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 bam, suddenly centripetal force, bam. Of course, it's the normal force from the track. It's causing that. It just opens up. Versus if you're on this teardrop shape, it plays out a little different. It goes like this. So I've got a flat part of the track right here. It's flat for a little bit, right? And then, guess this curve that's gradual? If I fit a circle flush to this curve, that's a big old circle with a big old radius. And if I look right here, this part of the track, that's like a medium-sized circle with a medium-sized radius. And then only at the very top, you guys see the very top, a little tiny circle can fit flush to that. So the radius is constantly changing. Okay, so the centripetal force builds up gradually, so it doesn't hit you all at once. Okay, a little bit of critical thinking right there. Okay, all right, I think I'm done with roller coasters. What do I have next lined up? Oh, that's right. I know what's next. All right. I'm going to build up to it. So you guys remember this was your lab. then I think I did mention this the other day too, is that, well, maybe more specifically, if you use a heavy mass especially, probably have something more like a conical pendulum where the string tension is not actually horizontal. This is more realistic, right? Right? Maybe it's some angle, okay? Now, take this picture and let's do a different application of this. I'm about to ask you guys a question about a car turning on a banked track, right? Right. Oh, now a car on a banked track, let's start with what if the road was not banked? What if the road was flat and you're trying to make a left-hand turn? You guys got that? The road's flat, you're trying to turn left. What external force is actually allowing you to make a left-hand turn on a flat road? Friction, right? Right. But what if you're in a state way up north where the road is all iced over and it ices over every winter and we got a bunch of cars and they all got to make this left-hand turn? Hey, what if you bank the road? Or even down here in Florida, you guys ever exit the interstate and the road is banked a little bit? Helps you make the turn without as much friction, right? And look at this free body diagram. I didn't even draw a friction force. Guys, how many forces do I have on this car? 2. There's the weight pulling straight down. And what other force? The normal force. You guys see the normal force pushing up to the left? Right? And guys, which one of those forces is the larger force? The normal force, right? Here's maybe a hint how you can figure that out. What if you were riding along, you're a passenger in this car, you're going along for the ride. You're going through, let's say it's a pretty sharp turn and the driver's driving pretty fast. Do you feel a little bit heavy or a little bit light? A little bit heavy, a little bit heavy. Kind of like if you're standing on a scale in an elevator and it's accelerating upward, the scale would read heavy. Right. Okay, so this normal force is greater than the weight. Ooh, guess that too? Right. And if I put these side by side, so conical pendulum, tension in a string versus car turning on a banked track, normal force. You guys see these free body diagrams look nearly exactly identical? Right? They both got the weight pulling straight down. They both got some kind of force up to the left. The tension pulls, the normal force pushes, but same idea, right? You guys see that? All right. Actually, these posters are really closely related to each other. Okay, you guys see that? Right, but we're going to focus on this car making a turn on an iced over road where there's no friction. No friction. Right? You're a road engineer one day, and you got to figure out how much should I bank the road. You guys got that? Now, I'm going to do 2 things with you guys. I'm going to walk you guys through this because I did kind of skip a step on this poster just to save a little space, but we'll go ahead and do this right here. And then I'll spit some numbers to you guys and see if you guys can solve this with numbers. So let's get a banked road. Guys, go ahead and draw this in your notes. This will be good practice right here. Let's throw in some angle theta. Okay, some angle theta. Let's draw a car right here. Maybe we should throw a title on this. Let's say car turns on banked road. Okay, there's a title for your notes. Okay, draw a car here. It's got some wheels. Draw a little license plate, some tail lights. Draw a rear view window. Okay, so we got that. So you guys know the car is going into the page, right? Like how you draw arrow going into the page, B going into the page. Okay. Car's going into the page, but because it's on a banked road, it's going to ultimately force it to turn to the left. Okay. Let's draw a free body diagram. Put a big old center mass dot. Okay. What's one force I told you was on this car? The weight, mg. Okay, and the other one's the normal force. Okay. What's a synonym for normal? Perpendicular. Right. Can you guys draw a line that's perpendicular to that surface? Okay. And make this a little bit longer than the weight vector. So however long that is, make this one a little bit longer. Show you guys why. Okay. So this looks kind of like an incline puzzle, but we're going to approach this a little bit differently than an incline puzzle. Because the inclines, remember the inclines I always told you guys, introduce a Cartesian system that's parallel perpendicular to the surface, right? Now this one you could solve like that, but I'm not going to do that because there's an easier way to solve it. I'm going to keep a Cartesian system that's parallel perpendicular to gravity. And so this normal force then I'm going to break into components and say this normal force is doing 2 different things. This normal force is holding the car up against its own weight, and it's also forcing the car into a left-hand turn. It's doing both of those things. Ooh, do you guys see a right triangle right here? A right triangle? And somebody tell me, what is this angle right here equal to? Is it the same as this angle down here? What if this angle was 31 degrees? How many degrees is this one? 31 degrees also. It's the same angle. That angle's that angle. You guys get that? Okay. Now, playing off triangle geometry, if the normal force, you guys see the normal force is the hypotenuse of that triangle? That means this leg right here is the normal force multiplied by what? Sine or cosine of theta? Is that sine or cosine? Cosine. Yeah, because we're translating from hypotenuse to the leg adjacent to that angle. That's cosine. Okay. Hey, does this also have to be exactly equal to the weight to balance out the weight? Is that what that is? Equals mg. Okay, or I should say that minus that equals 0, but you guys get the idea, right? Okay. What about this bit right here? Is this the normal force times what? Sine or cosine of theta? What's opposite of theta? Sine. Okay. And isn't that component actually driving the car through a circular loop? So what's the force called that moves something in a circle? Centripetal force. And what's the expression for centripetal force? mv squared over r. Right? Mv squared over r. Okay. Let's do some math out here. So I have two things. I have normal force times sine theta equals mv squared over r. I also have normal force times cosine theta equals mg. I really should back up a step and say normal force cosine theta minus mg equals 0, but then I can just slide over the mg and it just looks like that anyway, right? This is my system of equations. System of equations. Okay, you guys that? Got two equations. I know this is all in terms of variables. We're going to solve this one in terms of variables too. Okay. Yes, if you have a system of equations, is it a valid move? Are you allowed to divide one equation by another equation? Can you do that and get something that's still valid? Yeah, that's what I'm going to do right here. Put a big old fraction bar. I'm going to divide this equation by this equation. You guys ready to do that? Now, when you do that, what cancels out? Huh? Normal force. Goodbye. What else cancels out? Mass of the car. Right? And what is this? What is this right here? Because what is sine divided by cosine? What's that called? Tangent. Can you guys say tan theta equals, and say what does this consolidate to? You got a v squared over r, and I have a g down there. So that could look like that, right? Right? You guys see that? And that is that. Aha! It's the same thing. Look at that. Look at that. It's the same thing, right? Right. So now you guys see where it comes from? Right. Right. So now it's about to be math time. Math time. You're a road engineer, and you're told, I'll say, for example, let's say Earth gravity equals, we'll call it 10 meters per second squared. Let's say the radius of curvature of a road is 90 meters. Okay, so it might look like this from above. Here comes the road, it's straight for a while, and then it goes into a curve, and then it goes straight again. So it got straight, and then a curve, and then it goes back straight again. Okay, and so this bit right here is the curved part of the road. Maybe I'll hatch that in. Okay, say I just hatched in the curved part of the road. If I fit a circle flush to that curved part of the road, and I say, what is the radius of that circle? Who can tell me? What is the radius of that circle? What did I just tell you it's equal to? 90 meters. Radius is 90 meters. Okay, guess that big old 90-meter radius. Okay, got that? And I'll give you one more number. Let's say the speed limit is 20 meters per second. By the way, somebody asked me earlier. I looked it up. It's 45 miles per hour. I'll say 45 mph. But guys, are you guys going to do miles per hour in this class? No. So that's 20 meters per second. It's the same thing. Okay. All right. Question. How much should you bank the road? Go ahead and solve that. How much should you bank the road so that the drivers can make the turn even without friction? The road's all iced over. It's like December up north, road's iced over. But that's okay. They're all safe. All the cars are safe because you banked the road correctly. How much did you bank the road? All right, I got the number on my calculator screen. All right, who's gonna get this? How much gonna bank that road? Figured it out. 24 degrees. All right, Peyton got it. 24 degrees. Oh yeah. All right. So here, just start with this right here. Say tan theta equals, yeah, let's see, v squared over gr. So, right, I'll say v squared over gr. Right, so I'm using that as my formula. Let's get some numbers in here. Tan theta equals, right, so that'd be 20 meters per second. I'm going to square that. Divide by, I got 10 meters per second squared here. I got 90 meters here. Throw that all in parentheses. It's all in the denominator. Right? Then there's still one more step. Guys, if you want to extract this angle theta so that your last step says theta equals, because that's what I asked you, so what's the angle? Right? What's the last algebra step you have to do? Yeah. Okay. Who knows? Who knows the last algebra step? Inverse tan. Because that's how you undo tangent and solve for theta. You guys remember that a long time ago? Like if you have a 3, 4, 5 right triangle, how do you solve for theta? I said, well, do inverse tan, ratio of the legs, 3/4. And then, oh, hey, we're getting a 37-degree angle. You guys remember that from a month or two ago? Right? So that's all we're going to do right here. I'm going to do inverse tan of all this stuff. So what is all this anyway? 20 squared divided by 900. That's like 0.444. 0.444. Right. So it's inverse tan of that number. Let's do inverse tan of that, which is, yeah, 24 degrees. 24 degrees. There you go. So as long as you bank the road 24 degrees, right, and the cars are following the speed limit, then they should be able to make that turn even on an iced over road. Yeah. You guys got that? I got a follow-up question. Right? Because this is, guys, this is for a little car, right? You guys see those little cars? So you got a whole stream of cars. Zoom, zoom, zoom. They're all going. It's all working. Everything's good. Right. And then this guy comes along, a big old semi. Guys, this semi is like 10 times the mass. Guys, 10 times the mass. Uh-oh. Uh-oh. Guys, if you've got 10 times the mass, should I have angled this shallower, steeper, or the same angle? Same angle. How do you know the same angle? Because the mass canceled out. Yeah, mass canceled out. Canceled out right here. Yeah, mass is not part of the equation. Yeah, there you go. We didn't even plug in the mass of the car. All right. Got next for you guys. Let's do some Paul Hewitt demos. One's going to be a little bit of review, and then next one's going to link to the next thing I want to talk about. All right, Paul Hewitt time.
You travel faster when you're on the outside force or on the inside force. Do both forces travel at the same speed? Well, it turns out there's two kinds of speeds there. And we can see that with this little make-believe merry-go-round. If I draw a line, rotate the merry-go-round, we see that all parts of the line are traveling the same RPMs, revolutions per minute, yeah? But how about the linear speed, like in miles per hour? Outside or inside going faster? Well, let's put some people here. One here, one here, one here. These little pennies represent you, huh? I think you can see the outside part is traveling faster. If I whip it out a little more, yes, the outside one flies off. A little more. So it's the inside one that is going slower. That's physics. Yay. Tomorrow's space column might look something like this. You've been a great, big, huge tire, a couple of kilometers wide, and this thing be spinning at a constant RPMs. And people out here will walk around. If you took a regular balloon tire from a car or a bicycle, and you put some ants in there, and you just took the tire and you just dropped it off a cliff, what would the ants do? The ants would, they were just pretty fall. It would push against that thing. All the support's gone, and then just all fall. And they would say, hey, wow, someone got up and grabbed me, huh? But if you take that wheel, you spin it, and then you drop it, the ants will all get thrown on the outside, isn't that true? And the ants will think there's a force pulling them out. But no, it's a force pulling you in a circle. If all of a sudden it's a little hole there, you can't keep going. But the ant is pulled here. So the ants pull, pull, pull. People inside a space colony. There's people right here. Head, feet, okay? This thing's rotating like this. And these people are thrown against the outside rim. And these people think that there's a force pulling them out like this. They think that. And if you got one of those amusement type devices, those great big centrifuges, you ever get one of those guys? You stand up against the wall like this, okay, and they start revving around, and when it's going fast after that, they drop the floor out, and you stay there. And you stay there, you can hardly put your head over. You turn around like this, push-ups are hard to do, man, okay? Because you see yourself being pushed this way, but it's not happening. You're being thrown out down. Something pulls you in. So there's an inward force pushing in on you. You go, it's hard to put your neck out like that, it goes right back. Centripetal force, a center-seeking force. And that's what we'll enjoy tomorrow when we're in space vehicles.
All right, I'm gonna play this first one again real fast. It didn't capture on the video.
You travel faster. You have the outside force, the inside force. Both forces travel at the same speed. Well, it turns out there's two kinds of speeds there. And we can see that with this little make-believe merry-go-round. If I draw a line, rotate the merry-go-round, we see that all parts of the line are traveling the same RPMs, revolutions per minute, yeah. But how about the linear speed, like miles per hour? Outside or inside going faster? Well, let's put some people here. One here, one here, one here. These little pennies represent you, huh? I think you can see the outside part is traveling faster. If I whip it out a little more, yes, the outside one flies off. A little more. So it's the inside one that is going slower.
Right. Now that's in terms of a linear speed, right? So all those coins have the same angular speed, right? But they have different linear speeds. Let me play. All right, so I had to play it again because still trying to get used to my new tech here. Yeah, I got different. It works differently than my other system. All right, I think we're back. Yeah, we're back here. I think we're all on the same page here. All right, we're good here. So I have two posters for the two videos that I just showed you. So you guys saw the turntable. He was spinning that. Right. This was a couple of labs ago. We were doing this. Right. And one thing I'm showing with the equations on this poster is there's a connection between angular motion and linear motion. Guys, how do you go from angular motion to linear motion on a turntable? You very simply multiply by what? Radius. Boom, boom, boom. Right? As long as theta is in radians and omega is in radians per second and so on. Right? It has something to do with radians. Okay? Yeah, just multiply by radius. I'll tell you the linear values. How far have you gone around? How fast are you going? Like in a linear, right? Right. And then we're going to do a special application of this. If you want a term to Google, you can Google this one, O'Neill cylinder, like that. So say, hey, let's go in space. Let's have a big old ring in space. Right? Now, the only reason we don't have anything in space like this right now is it's just it's really expensive to get stuff into space, right? So there's only so much material we can get up there economically, right? Right. But in the future, like if we have more energy to work with, we're able to get more stuff there. So someday in the future, we'll have something like this, right? So you go into deep space, there's no significant gravitational forces around. Like maybe you see Earth way off in the distance, but tiny, tiny, tiny gravitational effect, right? So there's no like real gravity. Right? But if you give this a spin, hey, do you think you could be walking around on the inside and it could feel like you're walking around on a planet, right? Especially if this is big enough, it might be kind of hard to distinguish the difference between this fake gravity and this real gravity. Right? Now, you guys remember Newton's first law of motion says everything wants to, let's go to the mechanics of how this kind of works, right? Newton's first law of motion, doesn't everything want to move in straight lines if it's moving at all? Okay. Right. So to say in a curved path, because what actually is the force? What's the name of the force called that's holding you in? Centripetal force, right? And it's provided by what force in this case of this O'Neill cylinder? Is it a normal force from the wall? A normal force is acting as a centripetal force, isn't it? Isn't it? Right. What if that wall fell away? Or what if this turntable? What if friction disappeared? Or what if you had a ball on a string and you cut the string? Right. See if you guys get this. Right. So suppose this is spinning. Spinning. You guys see it spinning? Zoom, 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 spinning. Right. What if this was a wait a minute. Do I want to use this picture? Yeah, let's do it. Let's say suddenly it breaks friction and slides off. Right. Guys, which way would this one slide off? Is this here it comes around? Give you guys a couple options. Is this gonna suddenly make a 90-degree turn and fly straight away? Or is it gonna fly off tangent to its motion and go this way? Show of hands. How many guys think it's the second thing that I said? Second thing. Yeah, yeah. Or if I go way back to this lab. Let's do this lab. So here's your Play-Doh canister swinging around. Zoom, 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 zoom. Let's say you cut the string right here. Cut it right here. Okay. All right. So does this Play-Doh canister right at that moment make a sudden 90-degree turn and fly straight away? No. Does it keep going tangent to its path and keep going straight line that way? Yeah. Right. And then of course goes to projectile after that. Right. Like that. Okay. So how about this O'Neill cylinder? I think it might be the same story here about. Right? So remember, you're always trying to go tangent to your path. You're always trying to fly off the side, but there's a wall there blocking. I guess the floor in this case that's holding you. Right? It's holding you into the circular path. Right, centripetal force. Right. I wonder what is the connection between your centripetal force lab, you guys remember centripetal force, mv squared over r, and say like a rotating rigid body like this O'Neill cylinder, right? Where maybe it could be more convenient to use angular speed. Ooh, maybe that could be a good question. I'll ask you guys that question here in a few minutes after I finish explaining this. Right? Because suppose you know how big this is. I'll tell you, so many meters, so many kilometers radius. And let's say we want Earth gravity. So you can be walking around on the inside and it feels like Earth gravity. How fast do you have to spin it? And that's an angular velocity question. You could answer in radians per second. Right? So we need a way to connect this formula, mv squared over r, to this rotating O'Neill cylinder to solve for omega. And here's the connection right here. It's this one. It's this one. You guys remember this? Remember this? Right? All right, let's put it all together. You guys got your notes out? Let's do centripetal force equals mv squared over r. But you also know that velocity, or tangential velocity, is equal to angular velocity times your radial location from the center. So take that right there and substitute it right there. Let's say substitute. There you go, substitute. All right, you guys do that? All right. What's that going to look like? Centripetal force equals, okay, so I got m for mass. I got, no, I don't have v anymore. I have omega times r. Omega times r. Okay. Now let's still all be in squared. Don't forget that. And then divided by r. Okay. Oh, well, I can clean that up a little bit. So that could look like, okay, I got m for mass. I got the omega is going to be squared. This radius is going to be squared. And then it's all divided by r. One more step. What's my very last step? One of the r's cancels. You got the m, you got the omega squared, you got the r. All right, you guys see that? M omega squared r. Right. And that is exactly, right there. It's the same thing, right? And hey, what about all the people walking around? What if they have all different masses? Do you think they all experience sort of the same fake gravity field? They do. because if you divide by their mass, you get the centripetal acceleration. That's Newton's second law of motion. Right? Force divided by mass gives you acceleration, which is just simply omega squared times r. Okay, you guys got both of those? Okay. Something I want to kind of point out too. It's a little bit funny to think. This does make sense, but you have to think kind of deep on this. If you look at these two side by side, the ball on the string versus the O'Neill cylinder, right? One's in terms of linear speed, one's in terms of angular speed. Okay, that's all fine so far, right? Right. But look at the radius. How does the radius enter in each one of these? Right? Because this seems really weird until you think really deeply about it. But do you guys notice with centripetal force, the centripetal force is inversely proportional to the radius? The larger the radial size, the less and less centripetal force you need, less tension force you need, right? But with the rigid body like O'Neill cylinder, it's the opposite story. That's weird. Look at that. Now it's proportional to the radius, directly proportional. So now if you had an O'Neill cylinder that was like twice as big, it would be providing like twice the centripetal acceleration. That's directly proportional. That's weird, right? Or how about if you're walking up this ladder? It maybe makes more sense in terms of the ladder. Right. You guys see this guy climbing the ladder? He goes like, He's going to climb all the way to the center. Now he's at the center of the ladder. Hey, this is the axis of rotation. He's reached the axis of rotation at the center of this ladder that goes across the diameter. Okay. Guys, what does it feel like right at the center? How much gravity do you feel? Zero. Could you push off and you fly off into space? And you just fly off into space? Yep, that's what would happen. Don't let go. And here's the math that's going to back that up. If you have zero distance from the center, it doesn't matter how fast it's spinning, it's just going to zero out. Zero artificial gravity. Now let's climb back down the ladder. Now you can walk around on the ground level down here, and everybody experiences the same artificial gravity. All right, so one more puzzle today. You guys ready for the last puzzle? All right, here's the last puzzle. Call this O'Neill cylinder. O'Neill cylinder. Suppose I give you, let's do an artificial gravity. We're going to target 10 meters per second squared. We're trying to make everybody feel like they're on Earth. Right? So artificial gravity, 10 meters per second squared. What if I give you the radius of the cylinder is about 1 kilometer? And I want to know how fast do you have to spin it? Okay, so I'm giving you these two values. So given, right? We're targeting 10 meters per second squared artificial gravity. And I got a 1 kilometer radius. I said radius, right? Okay, 1 kilometer radius. I guess it's 2 kilometers diameter. I could have said that. 1 kilometer radius, same thing, right? How fast do you have to spin that? How fast do you have to spin that? All right, I got the answer. Who else got the answer? You're still working on that? You guys using, guys, what is gravity field? Is gravity field an acceleration value or a force value? It's acceleration, right? You guys think maybe this one right here? What's that? Centripetal acceleration equals omega squared times r. Maybe start with that. Now what? Hey, what are you going to plug in for centripetal acceleration? 10 meters per second squared? 10 meters per second squared we're targeting. We're solving for omega. That's how fast it's rotating. That's the question. So it's being squared there times. What are you going to plug in for radius? 1,000 meters. That's right, 1,000 meters. Because 1 kilometer is 1,000 meters. Let's do base SI units. Okay. Can you divide that over? 10 over 1,000. Is that like 1 over 100? And then there's one last step you have to do. Guys, what's the very last step? Square root. What's the square root of 1 over 100? 1 over 10 or 0.1? Okay. And one last thing, I need a unit. As this is 1 over 10, what? Radians per second. Yeah, because it's an angular velocity. How fast is it spinning? Radians per second. I go. Skipped a few algebra steps there, but you guys can figure that out. Okay, so 0.1 radians per second. Okay. So in the future, I bet something exactly like this is going to exist in the future. Okay. So in the future, we've got an O'Neill cylinder that's 1 kilometer radius. This is exactly how fast you want it to rotate. So 0.1 radians per second. Is that about guys, is that about 5.7 degrees per second? Can you guys see that thing spinning? About 5.7 degrees per second? Right? You guys see that? All right. Yeah, there's other questions you could ask too. Hey, I wonder how much time would that take to go around? But we're gonna hit a pause point today.